Today we are talking about 3.11, the last section before the midterm. Okay, it's hyperbolic functions. What is this all about? Okay, so hyperbolic functions, we're actually going to spend some time just talking about what these are, because these will be functions you probably will not have seen before, although you can study hyperbolic functions without calculus. Typically, you learn them at the point where you're in a calculus course, and that's fine. Okay, so we're going to just talk for a little while about what these things are, where they come from, and then, of course, we'll find the derivatives of these functions and that sort of thing. Okay, so here they are. The first is hyperbolic sine. All right, so the hyperbolic functions for every trig function, each of the 6 trig functions, there's an equivalent or like a corresponding hyperbolic function. Sometimes you hear these hyperbolic functions referred to as the hyperbolic trig functions. Okay, anyway, hyperbolic sine is defined like this. So the notation we give is sine with an h on the end of x. So hyperbolic sine of x is defined to be e to the x minus e to the negative x all over 2. Okay, so this is strange. We're calling it a new function. We're tying this one to the trig function sine, right? But it's the hyperbolic sine, yet it's defined in terms of these exponentials, e to the x, e to the negative x, and that sort of thing. What is this? Okay, so they're not trig functions, but we give them these names for a reason, and that's going to unfold here towards the beginning, before we get to the calculus on it. Why this would even be important, and then why would you give it a name attached to a trig function? What is up with that? Okay, just kind of receive this for now, and it'll unfold. All right, so that's hyperbolic sine of x, e to the x minus e to the negative x all over 2. Usually people don't say the formal name hyperbolic sine of x. Usually they just read those letters, and in this case people read that as sinh x, or the sinh of x. Okay, and I'll show you a quick picture. This is just a quick drawing of the graph. I would recommend, if you want a better picture of the graph, go into Desmos and just type in like y equals sinh x, S-I-N-H-X, and you'll see the graph. It'll know what you're talking about. It'll do it. And you even look graphically, like what's the connection between this and sine? Just the original sine x. You're like, well, it goes through 0, 0. So does sine, right? Sine of 0 is 0. Graphically, that's really the only connection. Okay, but we're gonna see more later. All right, what's up next? Well, of course, it's hyperbolic cosine. So hyperbolic cosine, the notation is cosine with an h on the end of x. And we just make a small adjustment. This one is e to the x plus e to the negative x all over 2. So we just turn that into a plus sign in the middle. Okay, weird. And this one, we don't have to, think of any new letters to kind of make sense of what that would sound like. We can just say cosh x for the hyperbolic cosine. Okay, and I'll give you a quick sketch of what this graph would look like. Y equals cosh x. And okay, like the only connection to the graph of cosine is that it passes through 0, 1. So the hyperbolic cosine of 0 equals 1 as well. And then it's got this shape, and that almost looks like a parabola, right? It's not a parabola. It's wider here at the bottom. Okay, so it kind of comes down and it flattens out much more than a parabola would. And then it comes up. Okay. And keep going. I'm not going to give you any more drawings or sketches, although please feel free, go into Desmos, sketch don't sketch, but have it, Desmos graph any of these for you. Never a bad idea. Okay, so the next is hyperbolic tangent of x, TANH of x. And, well, that's defined just like the trig functions are. Okay, now we're starting to see a connection. This is defined as sinh of x over cosh of x. And for the hyperbolic tangent, we want kind of a nickname for how to say that. And we're going to go with tanch, kind of like ranch. Okay, next up, cosecant, hyperbolic cosecant of x. Okay, and it's defined as 1 over sinh x, just like the corresponding trig functions. Now this one's got the most difficult name. Cosecant, hyperbolic cosecant, we're going to nickname that cosesh, like the secant will be sesh, so cosesh x. Okay. And, well, next up's got to be hyperbolic secant. And that's defined as 1 over hyperbolic cosine of x, or 1 over cosh x. And again, the nickname is sesh x. Kind of like, let's go have a study sesh. And we'll study sesh of x. Okay, next up, very last one, hyperbolic cotangent, COTH of x. That's defined to be 1 over tanch x, or you might even say cosh x over sinh x. And now this one also, we don't need to add any new letters to make sense of that sound. It's just coth x, kind of like moth. Okay. Before we go any further, a natural question is, how is this useful? How are these I mean, they're defined in terms of E, yet there's connection to trig. What's going on here? So without going into any details at all, I'm just going to present here 3 applications. Of course, there are many, many more, but I thought these 3 were kind of interesting. You don't need to know about these applications. I believe you do get a homework problem about this first one. You won't with these other 2, but I just want you to know, just so you don't think we're studying something that's totally pointless. Okay, so number 1, and probably the most well-known application of the hyperbolic functions, is the catenary. So the catenary is the shape, if you picture this wire that's hanging, I've got 2 telephone poles, right, and a telephone line hanging between them. The shape of that wire, or if you were to, hold up a string in a similar way between 2 points, the shape of that wire or that rope or string or whatever it is forms what we call a catenary. You would think that it might be a parabola or something, right? But it's not. Just the nature of the way that gravity will pull that, it depends on, the specifics of is it a wire or a string or whatever. But the way it'll kind of fall, it'll be much flatter here than a parabola would be, and then it'll curl up to the top. So if you wanted to describe that shape, you would have to use hyperbolic cosine, or cosh x. Now, this one has been flipped upside down. Has it been flipped upside down? No, that's right. Yeah. Cosh x made that shape. Now, what it might be is, stretched or shifted or something like that. Another really well-known example of a catenary is the arch in St. Louis called the Gateway Arch. You're familiar with that? So they wanted to design this arch, the Gateway Arch, so that it would be, very, very sturdy. And it turned out, it wouldn't, like, if there was any wind or anything, like, it'd be very stable. And so they realized the catenary is far more stable than, say, a parabola would be, architecturally. So the St. Louis Arch, it's got this kind of like a sort of a twist kind of happening to it, so it's pretty cool, but it's basically like this. Okay, so now that's the catenary flipped upside down. It's a terrible drawing, but all right, that's hyperbolic cosine turned over. So it's flatter at the top than a parabola is, and that just the way that all the weight kind of pushes down into the ends in the ground. Very, very stable. Okay, number 2, this one is pretty cool. The addition of velocities in relativity. And it turns out that uses hyperbolic tangent of x. What do we mean by the addition of velocities? So let's say a good example is you're in a train. Let's say there's a train going and you're sitting in the train moving along. And then you decide to get up and walk. And maybe you're going to walk forwards in the train. Okay, so you stand up from your seat or your booth or whatever, and you start to walk toward the front of the train. How fast are you traveling relative to the ground? Okay, so you would think, well, I'm walking, but also I'm being carried along by the train. So even before I started walking, I was already moving. So if I wanted my speed, my velocity relative to the ground, then I'd need to add those two velocities. How fast am I walking plus how fast the train is moving. Okay, and that makes sense. But when we look at things from a relativistic point of view, it turns out it's not that simple. So from the perspective of someone standing on the ground watching the train go by and you walking in the train, you would not be going as fast as just simply adding the velocities. And I know that sounds very weird. If you haven't studied relativity, it's fascinating. But all the math behind all this is totally accessible to us, especially once you get through calculus. But okay, so at the end of the day, to add those two velocities, you can't just add the numbers. You actually need to incorporate a hyperbolic tangent. Without any specifics on that. Okay. And then number 3, I think this one's kind of cool. It's called the tractrix. It uses hyperbolic secant of x. What's the tractrix? It's the path of an object as it follows another object. Okay, so think of tractrix comes from the root word we also use for trailer or tractor. So imagine, you've got maybe a truck and it's pulling a trailer. Maybe it's pulling a boat or something like that behind it. If you've ever driven a car with a trailer of any kind, you know that you can't just drive the car as if there was nothing behind you, right? The trailer doesn't follow the same path as the car or the truck. If you go to make a turn, you have to go really wide because that trailer is going to cut in. It's not going to follow the same path as the car. It's gonna cut inside on that corner. So you got to go really wide so the trailer doesn't run over something or hit a sign or something as you're turning. So the path of an object as it follows, if you wanted to to describe that path, then you would need hyperbolic secant of x. Okay, we've defined these, talked about some applications. We haven't even done any examples. That will be to come.